Hello, welcome to a video covering example 5 and the rest of the section 3.7 notes. So basically you want to start your notes at the top of page 4. And again, we see example 5 here, where the equation is y squared plus 2y equals 2x plus 1. And here we want the second derivative. So we're going to have to do it once and then do it again. So remember, this right here is the same thing as saying y double prime. We want to find the second derivative with respect to x. Now, we have been talking about implicit differentiation. So let's do the first derivative, get that out of the way, and then we'll worry about the second derivative. And remember, we're taking the derivative of both sides with respect to x. So we could also write like this, y squared plus 2y prime and 2x plus 1 prime. But remember, this is with respect to x. So if I fall through on it, the right side's easy. That's just 2. Because derivative 2x is 2, derivative 1 is 0. On the left side, that'll be 2y, but you gotta say dy over dx. And then plus 2, again you gotta say dy over dx. If you factor out dy over dx, you get 2y plus 2 equals 2. So dy over dx is simply 2 over 2y plus 2. And if you want to clean it up a little bit, you can factor out 2 from the bottom. And that just becomes 1 over y plus 1. So that's the first derivative. Now, we got to do the second derivative. So I didn't leave myself terribly much space here, so I'm going to kind of do it down here. But you should have enough space in your notes. So dy over dx equals 1 over y plus 1, which is also the same thing as saying y plus 1 raised to negative 1 power, if we want to avoid the quotient rule. Now, when I take the derivative again, so remember d over dx is the operation we use to denote the derivative with respect to x. If I take it again, I have d2y over dx squared equals, now we're going to have to use the power rule, sorry, the chain rule, negative 1 to the front, y plus 1 raised to negative 2 power, times the derivative of the inside. And our inside was y plus 1. Well, when I do the derivative of the inside, I have negative 1 over y plus 1 squared. Remember, y plus 1 to negative 2 power is y plus 1 squared on the bottom. Times the derivative of y plus 1 with respect to x. That's actually going to be just dy over dx. If we think about it, the derivative of y is 1, derivative of 1 is 0, but because you're taking the derivative of y with respect to x, you got to say dy over dx. Now, remember, dy over dx was more y plus 1 way over here. So I can just kind of sneak that back in. By the way, I think I'm supposed to say hi to Joey Cosland and Andy Woodruff. So, hello guys. Okay. So negative 1 over y plus 1 cubed. That's our second derivative. So it's just a little sneaky because you do the first derivative, which is even do that for a while for implicit differentiation. We do the second derivative, we know to do the derivative again. But because you're doing implicit differentiation with your first derivative, you're gonna have another you're gonna have dy over dx kind of be reintroduced. You gotta substitute for that. Okay. Now let's talk about the proof for the power rule. So this is kind of a pretty big deal because we know how the power rule works. We know it's just n times x to n minus 1 power. Fine. But we've never actually done a formal proof of it. And this is what we're going to do now. So first off, n, which is our exponent, right, can really be any rational number because we've had fractional exponents and done the power rule just fine. So n can be written as p over q, where p and q are integers. And remember, n is a rational number, and we'll assume for now that q is greater than 0, assuming that p could be negative if we want it to be. Okay, so if y equals x to the n, y equals x to the p over q power. Now, one thing that we could do to get this problem started is we can rewrite our problem in this manner. So think about what I just did. We have y equals x to the p over q power. Remember, we replaced n with p over q. And I can deliberately raise both sides to the q power. So raise both sides to the q power. If I do that, of course I get y to the q power equals x to the p power. Okay. So now we guarantee that our exponents are all integers. So if I do the power rule, so if I take derivative of both sides with respect to x, this is going to be q times y to the q minus 1 power. But remember, we got to say dy over dx equals p times x to the p minus 1 power. Okay, if I get dy over dx by itself, I'm going to have p times x to the p minus 1 power over q times y to the q minus 1 power. Okay, we're going to have to need a little more space here. So let me kind of lasso this. Okay. So if I keep going at this, I can do a little bit of rearranging. Remember, we knew that y to the q had equaled x to the p. So of course, y to the q minus 1 equals x to the p minus 1. Is that correct? Hold on a sec. Actually, this is what I'm going to do instead. Again, we know that y to the q equals x to the p. But instead, I'm going to do this. Y equals x to the p over q. Okay, now I'm going to substitute. P times x to the p minus 1 over q times x to the p over q minus 1 power. The reason why I'm doing that is so that I have just x's to look at. And I think you could probably realize I'm going to use some of the properties of exponents afterwards. So I can kind of separate off the p over q and keep the focus on the x's, x to the p minus 1 power and x to the p over q times the q minus 1 power. So p over q times q minus 1 is the power for the bottom. Now, if I subtract my exponents, right, that's what we do. P minus 1 minus bracket. And if I distribute the P over Q into Q minus 1, I'm going to give P minus P over Q so it's P over Q times X P minus 1 minus P plus P over Q. Of course, those cancel. So I'm getting P over Q minus 1. And remember, N had equal P over Q earlier on, right? Way up here. And so we wind up just getting that. And now we've actually proven the power rule. Sorry that was a little bit choppy there. It's a little bit of a tricky proof, but just something that's kind of cool to do. And as you know, you're probably going to be asking, is this going to be on the test? No, I'm not going to ask you to prove the power rule on the test, but just cool to see. Okay, so now we got 4 more examples, and this is a good opportunity to kind of try these on your own. Just kind of a little practice, just make sure you're comfortable with implicit differentiation, or just doing derivatives in general using the power rule. Actually, never mind. These are not implicit differentiation. I was correct. Just simply power rule. So you may want to pause the video, or if your plans for the whole class, one can come up and pause it. If you do the first one, you should get this. Do the next one, you should get 7 times 2/7 times x in negative 5/7. Over here, 4 times negative 3/4 times x in negative 7/4. So basically, you could do this for any rational exponent. That's kind of the whole point of this. Times x in negative 3/2. Clean it up a little bit. Negative 3 times x, negative 7/4 minus x in negative 3/2. And lastly, I'll probably rewrite this one as 4. 3x to the 2/3 plus 5 raised to negative 1/4 power. So y prime is 4 times negative 1/4, 3x 2/3 plus 5, negative 5/4. And the times root of the inside, which will be 3 times 2/3 times x and negative 1/3 plus 0. And if we clean that up, there's a lot happening here. That should just be negative on the outside, 3x to the 2/3 plus 5 raised to negative 5/4 times 2 times x raised to negative 1/3 power. So that concludes page 4 of the section 3.7 notes.